Transformation of system of linear coupled differential equations into coupled first order equations. The problem I'm discussing today is just the main thing is to try to transform coupled differential equations that are of a higher order than first order into a set of first order differential equations that are coupled that could easily be solved by analytical methods or numerical methods. Well, here's the two problems, which are two coupled differential equations that are non-homogeneous. The first equation is second order, and the second equation is third order. So typically when you look at this equation, the first thing I looked at is, at least in the second equation, is try to integrate both sides. When I tried to do that, that didn't work out. So there's a transformation that is normally used that works. They'll simplify this equation, but there are further things that you look at that makes the even putting in first order makes the problem still somewhat complicated, but a little bit easier to deal with. So we'll look at that. So here's below are the equations, 5 equations that are the transformations. And these equations are broken down into 5 first order differential equations. So using those transformations, we get, okay, here are the 5 coupled equations. They're still coupled. The second one and the fifth one are inhomogeneous. So where do you start here? Yes, you could use numerical methods, but you need an initial condition. So I decided to use matrix methods here, which I separated the left side of the equation and the right side of the equation and put them in matrix and column vectors, which you'll see in on the next chart. So looking here, here's the matrix problem, which we have the column vector is the forcing function. And typically what we need to do here is ignore the forcing function and solve the homogeneous problem, which is the column vector on the left side equation equal to the matrix times the column vector. That's what we need to look at. And here's the problem that I'm talking about here. You see the right side of the equation here. This here. And this is column vector represented. So we need to find the eigenvalues and eigenvectors of the matrix to get the homogeneous solution. Okay, we calculate the eigenvalues for the coefficient matrix. We get 5 eigenvalues because this is a 5 by 5 matrix. So, but in this case, we get complex values here, and then we got conjugate. So if you get an I, you should be getting a minus I or some conjugate of the complex number. So we got 5 eigenvalues here. And when calculating these eigenvalues, we get these eigenvectors. So we have the homogeneous solution of the homogeneous problem. So next we can calculate, if we got a homogeneous solution, we need to find the particular solution. So here at the top equation, we got the solution to the homogeneous problem. Now typically with the complex values, see all these complex values here, these can be converted to sine and cosine. I didn't do that here because this problem seems to be a little unique, and that's what I do. You know, try to deal with these kind of unique problems. So I didn't want to do that. So I played it safe to use exponentials, the complex exponentials. But I came up with a fundamental matrix, which is here, and we can find the solution to the problem uh, by the particular solution by this equation, this matrix equation. One problem, this matrix is not invertible. So when you calculate the determinant, it's equal to 0. So it can't be inverted. So what can I do next? What can I do to solve this problem? What is the particular solution? So what I did was I had to do things the old-fashioned way. I substituted the particular solution, one of the part of the particular solution, into the equation to try to find the coefficients that satisfy that condition. So I did that, and I solved for the five unknowns, five equations, five unknowns, and I got the particular solution. Now, using the t squared plus 1, I could not find a solution or anything that satisfied the conditions, which that was any coefficients that satisfy the conditions. So that did not work. So as far as finding unknown parameters, that I couldn't find anything. So you see that here. I couldn't find a column vector to satisfy that condition. So I did get I found a particular solution. I'm not going to say that's the only solution, but that solution does satisfy that equation. And using a superposition principle, it works because this is a linear system, not a nonlinear system. So superposition applies here. This is the total solution I got for the problem that satisfies the condition. That's not including t squared, the column vector t squared. And in fact, I separated. You can separate the e to the t and the t squared plus 1 into separate column vectors. So I couldn't find a constant to do that. Now, that's not to say that there's not another way to do it, another solution to it, but in this case I didn't. I found a solution, and finding a solution is a good thing. So I just thought this was an interesting problem. Subscribe to my channel. Any comments about this problem, any suggestions, any other things that could be added to help out, please leave it in the comments. Click a like button if you like it. If you click a dislike you don't like it, and tell me why, and I will try my best to accommodate.